In this video, we're going to introduce a new quantity called momentum. Let's motivate this a little bit. When we introduced work and energy, we found out after a little bit of manipulation that there was a global energy conservation law, and that was very powerful for dealing with certain situations, mainly before and after, or when there's a force that depends on position that gives rise to a position-dependent potential energy. So we're attracted to the idea of these conservation laws now, and we have a natural question if there are any more conservation laws out there in nature that give us a similar increase in our power to solve problems or explain situations. So the next one we'll find is called momentum. And the definition of momentum is quite simple. For an object with a mass m moving with a velocity vector v, we take the product of those to get its momentum. The symbol for momentum is p, and it is a vector. So it's always parallel. The momentum is always parallel to the direction of motion, just like velocity. And the momentum is larger if the object has more mass. Now, what's the point of momentum? Well, we're going to go through a couple of derivations here to show how momentum can be useful. The first one is we want to relate momentum to Newton's first and second laws. Let's just recall for a moment what those say. The first law says that an object that is free from any external force will travel with a constant velocity. So if there's no net external force, then the velocity of the object is constant. And for the second law, if there are applied forces, then the vector sum of all force vectors is something that determines the acceleration, right? Sum of forces equals mass times acceleration of that object. So in terms of momentum, the first law doesn't really change what it says. If the velocity of an object is constant, then its momentum is automatically constant as well. So this actually matches up quite well with our colloquial usage of the words force and momentum. If an object has a lot of momentum, it's difficult to change its momentum. You say like a sports team or a business has built up a lot of momentum, and it's going to require a lot of force to change that. We see the same interpretation echoed in the second law. Let's write out the second law in terms of velocity instead of acceleration so we can see the relationship to velocity. Its sum of forces is equal to the mass of the object times the rate of change of that object's velocity. Well, the mass of a single object is going to be a constant, so it doesn't matter whether we multiply by the constant before the derivative or afterwards. So these two things are completely equivalent. But what's sitting in the parentheses right here is just m times v. That's the momentum. So we get a Newton's second law that says the rate of change of momentum over time is equal to the sum of all forces acting on an object. We don't see the mass appear explicitly in here, but it is living inside of the definition of momentum in some way. But sometimes it's convenient to just have a formula that relates the force directly to a quantity without this proportionality coming into play. So our second law says the rate of change of momentum over time is equal to the total force applied to that object. This relationship between momentum, time, and force lets us solve certain questions about how much force is applied during an impact, or how quickly an impact occurred if it had a certain change in momentum, or those sort of things. Let's see how those get set up into a simple equation. I'm just going to rewrite this as the rate of change of momentum on the left and the total force on the right. In this equation, we can integrate both sides from some initial time t0 to some final time t1. And here we're thinking of the force as a function of time, so a time varying force, t1. On the left side, the integral of a derivative just turns into a difference. So p, momentum at time 1, minus p0, the momentum at time 0. But this right-hand side can't be simplified unless we know something specific about this force versus time function, right? The integral could literally have any behavior. But what we can do to get this into a usable form without knowing a ton of details about the force is to realize that when we take a function and integrate it over some interval, then that gives us basically the definition of the average value multiplied by the time interval. So if it's acceptable to talk about only the average force during that time interval, then we don't have to do an integral or nor any details about the force. We just speak of its average strength. And this can still be useful, right? You might want to know the average strength of one impact versus the average strength of some other impact. So we get an equation where the change in momentum is proportional to the average force and the interval of time over which it acts. For an example of how this equation would be used, let's do the following problem. A high-speed video of a golf shot shows the ball starting from rest and leaving at a velocity vector of 10 meters per second in x, 40 meters per second in y. The club was in contact with the ball for 15 milliseconds. The ball has a mass of 200 grams. What was the average force that the club applied to the ball? So here we're looking for the average force vector. And that could be found from this by dividing both sides by delta t. And the change in momentum here is due to the change in velocity. Momentum is mv. So my change in velocity is this final velocity here, leaving at, and the initial velocity, which is 0. So I'll just have v, as given by the problem, minus 0 for an initial velocity, all divided by delta t. So let's plug in our numbers here. 200 grams is 0.2 kilograms. The velocity vector remains as a vector, 10 meters per second, 40 meters per second. The time interval, 15 milliseconds, is equivalent to 0.015 seconds. And if I put all those numbers together, I get a force vector of 133 newtons for x, 533 newtons for y. So that's the average force of the club head on the ball. It's a way to get an estimate of how hard a hit is. Notice that it depends on the mass of the ball, its change in velocity, and the interval of time. So if somehow the club and the ball were, say, more rigid or more brittle, and the time duration was lower, the force would have to be much higher to generate the same change in momentum. If the club and the ball were like squishy or elastic or rubbery, then this time duration would be longer and the force overall on average would be less. So these questions of force don't depend solely on how hard, how big the change in velocity is or how big the object is. They also depend on sort of how quick the collision is. Our second main reason for introducing momentum is that it turns out to be a conserved quantity, and we can prove this by expressing Newton's third law in terms of momentum. Let's recall what the third law says. if we have two objects, M1 and M2, which interact with each other in some way and produce a force on each other due to that interaction, if M1 experiences a force F12 due to the interaction, and M2 experiences a force F21 due to the interaction, then F12 and F21 must be opposite vectors of each other. The third law doesn't tell us anything else about the interaction except that these two vectors must be opposite. They could be large or small at weird angles to the line between the objects. Anything goes as long as they're opposites. So now let's express Newton's third law in terms of momentum. To do this, I'm going to form a quantity that I call the total momentum of the system. The total momentum is always defined as the sum of the momenta of each object that's considered to be in the system. So here with two objects, I'll have momentum of object 1 and momentum of object 2. So in terms of mass and velocity, this could be expanded as mv1 plus mv2 as a vector addition. What I'm going to show here is that the time rate of change of the total momentum here is 0 if there's only an internal force acting. Let's go through that proof. It's actually quite quick. The derivative of the total momentum is clearly equal to the derivative of P1 plus the derivative of P2. And because of Newton's second law, remember dp dt equals F in general, the rate of change of momentum 1 is equal to F12, and the rate of change of P2 is equal to F21. But the third law guarantees that these two vectors are opposites of each other, so when we add them together here, we get 0. So that completes the proof that the total momentum of any system of two particles interacting never changes due to the internal forces. Now let's try to expand this to a more general case. Let's try to do the same derivation for a system of 3 or more objects. I've drawn 3 on the board, but we'll generalize for an unlimited number of objects. Let's label them by M1, M2, M3, and so forth. In general, we'll have M with a subscript of I, where I is the number index of the object. Between each of these objects, there could be some interaction. Say between M1 and M2 there's an attraction. We'll label that as F12 acting on mass 1 and F21 acting on mass 2. So the object that feels the force is the first subscript, and the object that causes the force is the second subscript. Let's assume in general that there's interactions between every pair of particles in the system. So we have F13, F31, and these interactions don't always have to point straight together. They could be repulsive, attractive, or at some skew angle. So let's indicate that possibility by drawing the arrows for M3 and M2's interaction in a different direction. This will be F32. 3 feels the force due to 2. And this will be F23. So these are the 6 possible internal force vectors. Now let's also generalize a little bit further and say that if there are any forces on these objects coming from outside the system, we'll classify those as external forces. So Fe1 will be an external force on object 1. Fe2 is a possible external force on object 2, and Fe3 on object 3. And we want to remember that this could be generalized to an unlimited number of objects. We would just have a series of internal forces with 2 subscripts and a series of external forces with 1 subscript. So let's collect these terms a bit here and introduce our notation. So the momentum of the I particle, so I will indicate the number of the object. The momentum of the ith object is its mass times its velocity vector, right? 1-to-1 relationship between a velocity vector and a momentum. For each individual, there's a vector there. Yeah. For each individual momentum, its time rate of change is set by all of the forces that act on it. So here I'll have a sum over, let's say, a different index j of the forces with the subscript ij. So this means if my I index is set to 1, I'm looking at all the internal force contributions that have the first subscript as a 1. So I would sum up 1, 2 and 1, 3. There is no F1, 1 because an object can't create a force on itself. So this is all of the internal forces right here. Internal. The external force will be F, with the first subscript being E for external, and the second being the index of the particle, so I. Right? That would give us Fe1 if we were talking about particle 1. So I and j could be any object in the whole collection, even if there's more than 3. So we've got a sufficiently general notation here. So those blue terms there count for external forces. Now our claim in this what we want to show is that the change in the total momentum of the system, the rate of change of the total momentum, is only influenced by the external forces. The internal forces make no difference towards the total momentum. So let's see how we can prove this. First thing to realize is that the total momentum is defined, as it always is, the sum of the vector momenta of each object in the system. So if we take the time derivative of our definition to find out if the total momentum is changing or not, we can just add up the derivatives of each of the individual momentum. And from our work up here with the notation, the derivative of the momentum of one of the objects is equal to this sum over the other objects, j, plus the external forces. Okay? Now this term here in the middle, this term here in the parentheses can get split up. So let me get some room to continue this proof. So now we have a sum over indices I and j of all of the internal force possibilities, I in the first, subscript j in the second. That comes from this. And then the second term in parentheses is just the sum over index I of all the external forces acting on the objects. Now let's focus on this second term here, because this is the one that's due to internal forces. And think about what this means. We have two indices here. So I goes over the particle feeling the force, and J goes over the particle causing the force. So we can think of the Fij's, let me look like this. We can think of the Fij's as living on a grid, right? Where the rho represents the particle feeling the force, and the column represents the particle causing the force. So we might get something here. So here would be F12, and here would be F21, and here would be F13, and here would be F31, and here would be F23. Rho is for particle 2 feeling the force, the column is for particle 3 causing it, and here would be F32. And if we had more objects in the system, then we would just continue with this pattern. Zeros along the diagonal, and then this mirror image across from top right to bottom left. Now the sum here says we just have to add up every number in this grid, right? So we'll just add up all of these things. But then what Newton's second law says, what Newton's third law says, is that these entries with F21, F31, F32, these must be equal to the opposites of the forces with the subscripts reversed. So now we see that every entry on the top right half has a negative pair on the bottom left half. And so if we add up all of the numbers in the whole grid, it will always be equal to 0. So this term here, as complicated as it looks, sums up to 0. So then our claim is proved. The time rate of change of the total momentum is only equal to the sum of all the external forces on the system. Okay, so this gives us two important qualitative conclusions. We don't usually use this to do some calculation like figuring out the derivative. We don't usually use this. It's more of a conceptual tool to get important conclusions that we can then use to start our application to realistic problems. But those qualitative conclusions are, if you have a system of many, many particles and you treat them all as one thing, right? Like, say, all of the atoms in a basketball. They're all different atoms. They're all pushing on each other. They're all vibrating and stuff. But all of those internal forces, no matter how many of them there are or what weird laws they obey, those internal forces don't amount to anything when we consider the overall motion, the overall momentum of that basketball. It's great. It reinforces something we've been doing all along, taking a block or a brick and just saying it has one velocity, one position. We don't need to worry about all of its parts, and we have now here a proof that all those parts cancel out. The second important conclusion is that if we want to consider an object's motion under the effects of external forces, then we don't need to worry about which part of the object the external forces pull on or push on. We just add up all the external forces on an even basis. They all get treated equally. So if we have an object composed of many different, say like 40 magnets in a magnetic field, we don't have to worry about where each one is or how strong each one is. If we just know the force on each little magnet inside the big one, we just add up all those forces and get the total force. That's what determines the motion. So this provides another justification for something we've been doing all along, is we say, oh, here's a cart on a ramp. We'll just say that its gravitational force is mg. But what about the force on the wheel versus the spring versus the axle versus the body? None of that matters. Just the total force matters. So we can really simplify that. What about the normal force? Well, it only pushes on the wheels, not on the axle, not on the body, not on the decorations. So Do we have to worry about that? No. Doesn't matter what part of the object the external force pushes on, we can just throw it all in the same bin and add it all up and just treat it as one total external force. Now, conservation of momentum is a very grand principle. It can be difficult to actually use it in a specific situation with if there were 5 particles and all these different forces, you'd be pretty much at a loss or really wasting a lot of time going through that tedium. But we can observe its effects in a simple situation. We boil it down to really the essence of what conservation of momentum is doing. We can still understand it without going through all of the mathematical difficulties. So we usually will see this applied in problems where there is a brief interaction between 2 objects that we call a collision. We'll discuss collisions specifically in a future video. Right now, we're just going to lay down the basic equations that conservation of momentum would provide to us to analyze a situation like a collision. So let's say there are 2 carts, or any 2 objects, that move along a frictionless surface in one direction, either to the right or to the left. And there's some potential for interaction between them, so I've drawn this little spring bumper on mass 1. So if these 2 carts got too close, they would effectively repel each other. And like conservation of energy, conservation of momentum is going to give us a way to relate what's going on before the interaction to what's going on after the interaction, right? This quantity called total momentum stays constant, so we can use it as a great way to relate the before and after. So let's take what I've drawn right here as a before situation. Giving quantities that occur before the collision a subscript 0. So the total momentum subscript 0 before the collision is m1 times v10 plus m2 times v20. Actually, I don't need the vector symbols right now because everything is only in the x direction. It's all x components. All right, so if these objects are moving in a way that will eventually bring them together, so here I've drawn V1 as a little bit larger than V2, so mass 2 might eventually catch up to mass 1 might eventually catch up to mass 2, and they bump together. Right. Afterwards, we might have a situation then where mass 2 is moving at a due to the interaction, due to the collision, mass 2 ends up moving at a different velocity, and mass 1 ends up moving at some different velocity as well. So for after the collision, I'll use the subscript f, so we have v1f and v2f. Then the total momentum after the collision will be m1 v1f plus m2 v2f. And we can't really predict the exact values of these 2 final velocities without knowing the details of the force, but we do get at least one equation from conservation of momentum. That is, the total before and the total after must be the same. So m1 v10 plus m2 v20 equals m1 v1f plus m2 v2f. So if the track is frictionless and there's not like an external force of wind or a magnet or something, the only force is the internal spring between these 2, then this equation coming from conservation of momentum will always apply, no matter if the carts are before a collision, during a collision, or after a collision. This equation gives us a relationship between four variables, right? V1, V2 before, V1, V2 afterwards. So it's only one equation. So we can't completely solve a collision, as in we know what is going in, we know all the initial values, and we want to predict all the final ones. We can't solve that exactly using conservation of momentum alone, but we can give a family of answers, right? V1, if it was known, would require a certain value of V2. If V2 was known, would require a certain value of V1. We can reduce the possible values of V1 and V2F to those that satisfy conservation of momentum. So let's do a quick example showing how this works. I'm going to make up some numbers for the masses of the carts. Let's say M1 is 4 kilograms, M2 is 1 kilogram. I'll make up some initial velocities. V1, 0 equals 2 meters per second, and V2, 0 equals, let's say, 0.5 meters per second. I'll make up that I measured one of the final velocities. Let's say I measured V2, 0, V1, F, so the velocity of cart 1 after the collision. Let's say I measured this to be 1.5 meters per second. And so the question is, based on these knowns and this measurement, how fast must cart 2 be going after the collision? So our technique here is to apply the conservation of momentum equation. See if it allows us to solve for the value of V2F, or if we need to put in some more information. First, I'll calculate the total momentum before. 4 kilograms for M1, 2 meters per second for M1, 1 kilogram for M2, 0.5 meters per second for M2. So my total momentum is 8 plus 0.5, so 8.5. And our unit of momentum is just kilograms meters per second. There's no better name for it than that, unfortunately. Now that we've got the total momentum, we know, since there's no external forces and no friction, that this is the same total momentum at any point of the motion. So I can equate this to the final velocity values. So 8.5 is the total. Mass 1 is 4. V1 after the collision is 1.5. Mass 2 is still 1 kilogram. And V2F is a variable, it's unknown. So let's just work on simplifying this then. Four times 1.5 is 6. So I can get rid of the kilograms on all the terms by dividing by the unit kilograms, or dividing by 1 kilogram everywhere. So I got 8.5 equals 6 plus V2F, so that means V2F must be 2.5 meters per second. All right, so I can predict partially the result of the collision. If I know one of the values, I can predict the other final velocity.